No spacecraft has visited Uranus since 1986. That single flyby is still the only close-up look anyone has ever gotten. Nobody planned to revisit that data. Then a NASA physicist, trained on a completely different planet, went back and reopened the old files anyway. Something in there didn't add up. William Herschel spotted Uranus through a homemade telescope in his backyard in Bath, England in March 1781. He first thought he had found a comet since it moved slowly against the background stars and looked fuzzy rather than sharp like a normal star. Only after other astronomers tracked its orbit for months did anyone realize it was a full planet, the first one discovered in recorded history that ancient civilizations had never named or worshipped. Herschel wanted to name it after King George III, but astronomers across Europe eventually settled on Uranus instead, keeping with the tradition of naming planets after Greek and Roman gods. Uranus sits about 1.8 billion miles from the Sun, roughly twice as far out as Saturn, and it takes 84 Earth years to complete one full orbit. It is classified as an icy giant rather than a gas giant like Jupiter or Saturn, since its interior is made mostly of water, ammonia, and methane ices surrounding a small rocky core. From Earth, it just looks like a plain blue-green dot, calm and featureless compared to Jupiter's storms or Saturn's rings. Ancient stargazers in Greece, Rome, and China never recorded Uranus as a planet, even though it's technically faint enough to see with the naked eye on a clear, dark night. It moves so slowly across the sky, taking 8 decades to complete one lap, that nobody before Herschel ever noticed it wasn't just another background star. That slow, quiet motion turned out to be a fitting first impression, since the planet's reputation for centuries afterward stayed just as calm and unremarkable, right up until Voyager 2 actually got close enough to look. That calm appearance is exactly what made the 1986 flyby such a shock, because the data that came back described a planet behaving nothing like its quiet reputation suggested. Voyager 2 launched in August 1977, originally built to study Jupiter and Saturn. It flew past Jupiter in 1979 and Saturn in 1981, and both flybys went well enough that NASA engineers realized a rare planetary alignment would let the spacecraft keep going, swinging past Uranus and eventually Neptune as well. Something that only happens once every 175 years or so. After a lucky planetary alignment allowed engineers to extend its mission, the spacecraft kept flying outward, reaching Uranus on January 24, 1986, 9 years into its journey. It remains the only spacecraft in history to ever visit Uranus up close. No orbiter has circled it. No lander has touched one of its moons, and no probe has been sent back since. Everything scientists know about this planet's magnetic field, its radiation belts, and its moons comes from that single 5-day pass, gathered while the spacecraft was moving too fast to do anything but snap a quick set of readings before continuing on toward Neptune. During those 5 days, Voyager 2's instruments recorded a magnetic field tilted 59 degrees away from the planet's spin axis, offset from the planet's actual center by about a third of Uranus's radius. No other planet in the solar system has a magnetic field shaped like that. The spacecraft also found intense electron radiation belts, among the strongest ever measured anywhere, sitting inside a magnetosphere that was almost completely empty of plasma. Scientists nicknamed it a vacuum magnetosphere because of how hollow it looked. For decades, this combination of a lopsided field, empty plasma, and violent radiation became the accepted description of what Uranus is actually like. Nobody had reason to question it, because nobody had any other data to compare it against. A magnetosphere works like a protective bubble around a planet, built from its magnetic field that blocks the solar wind, a constant stream of charged particles blasting out from the sun. Earth has one, Jupiter has one, and so does Uranus. What confused scientists about Uranus's version was the radiation belts. Intense electron belts, like the ones Voyager 2 recorded, need a steady source of energized particles to keep them charged up. But the surrounding magnetosphere was almost empty, with no obvious plasma source anywhere nearby to explain how those belts were staying so active. It was like finding a raging fire with no fuel supply feeding it. This contradiction bothered Jamie Jasinski, a space plasma physicist at NASA's Jet Propulsion Laboratory, for years. Jasinski had previously worked on NASA's Messenger mission to Mercury, which orbited that planet for 4 years and collected thousands of individual passes through its magnetic environment. During that mission, he noticed that solar activity occasionally stripped Mercury's magnetic field down to almost nothing for brief stretches, only for it to return to normal shortly after. Before we move on, if you're enjoying this analysis, please consider subscribing. It helps the channel tremendously. That experience planted a question in his mind about Uranus. Voyager 2 only got one shot, lasting 5 days out of an 84-year orbit. What if that one shot simply caught the planet at an unusual temporary moment instead of showing its normal, everyday state? Jasinski and his team went back and reanalyzed solar wind measurements. Voyager 2 collected in the weeks leading up to the Uranus flyby, data that had mostly sat untouched since the 1980s. What they found was published in Nature Astronomy on November 11, 2024, and it rewrote the story completely. In the 2 weeks before Voyager 2 reached Uranus, the solar wind pressure upstream of the planet was unusually low and calm. Then, just days before the spacecraft's closest approach on January 24, 1986, the density and speed of the solar wind spiked sharply and kept climbing right through the encounter. That spike squeezed Uranus's magnetosphere down to roughly 20% of its normal volume, compressing it like a sponge under pressure. According to the team's modeling, this kind of compressed, plasma-starved state only happens at Uranus less than 5% of the time. As Jasinski put it, if Voyager 2 had shown up just a few days earlier, the solar wind pressure hitting the planet would have been about 20 times lower, and the spacecraft would have measured a completely different magnetosphere. In other words, the single most influential dataset ever collected about Uranus captured the planet during one of its rarest, most unusual moods rather than its typical everyday condition. That single mistimed visit didn't just confuse scientists about the planet's magnetic field, it also changed what they believed about the moons orbiting right alongside it. Uranus has 27 known moons, and the 5 largest, Miranda, Ariel, Umbriel, Titania, and Oberon, were all studied using the same 1986 flyby data. Because Voyager 2 found almost no plasma surrounding the planet, scientists concluded decades ago that these moons had to be geologically dead, with no activity venting gas or particles into space around them. That conclusion helped shape which worlds NASA considered worth another visit and which ones got written off as boring, frozen rock balls not worth the fuel. The new findings flipped that assumption. If the missing plasma was actually caused by a temporary solar wind event squeezing the magnetosphere and driving material out, rather than reflecting how things normally look, then the moons might not be as inactive as everyone assumed. Some of these moons show surface features, like Miranda's oddly jumbled, cracked terrain, that already hinted at past geological activity even before this new study came out. Ariel also shows long, deep canyons across its surface, features that many planetary scientists have long suspected point towards some kind of internal activity rather than a completely frozen, dead history. Researchers now say it is possible these moons could be venting material into space on a regular basis, material that Voyager 2 simply missed because it arrived during an unusually empty, swept clean moment. That possibility matters even more given how many icy moons across the outer solar system, from Europa at Jupiter to Enceladus at Saturn, have since turned out to hide liquid oceans beneath their frozen crusts. If Uranus's moons turn out to be similarly active, they would join a growing list of small, icy worlds that look boring on the outside, but hide something far more interesting underneath. That question about the moons ties directly into an even bigger, stranger fact about Uranus itself, one that has nothing to do with magnetic fields at all. Every planet in the solar system spins somewhat upright, tilted a little compared to its orbit, but still roughly the same way as its neighbors. Earth tilts about 23 degrees. Uranus tilts about 98 degrees, past, sideways, and slightly upside down compared to the rest. Instead of spinning like a top, Uranus rolls around the sun like a ball, with its north and south poles taking turns pointing almost directly at sunlight during different parts of its 84-year orbit. Nobody knows for certain why Uranus ended up this way, though the leading explanation among planetary scientists is a massive collision, possibly with an object roughly the size of Earth, sometime early in the solar system's history. That kind of impact could have knocked the young planet completely off its original axis and left it spinning on its side ever since. Some researchers have even suggested the collision could have happened twice, with two smaller impacts adding up over time rather than one single catastrophic hit, though that idea remains far less settled than the basic collision theory itself. This extreme tilt also creates seasons, unlike anywhere else in the solar system, with each pole getting roughly 21 years of continuous sunlight followed by 21 years of continuous darkness. During Voyager 2's 1986 flyby, one pole happened to be pointed almost directly at the sun, meaning the spacecraft caught the planet during one extreme of its long, unusual seasonal cycle rather than during more typical in-between conditions. That sideways spin, combined with the planet's unusual magnetic field, made Uranus already look like an OD ball among the planets long before the 2024 solar wind discovery came along. But the tilt isn't the only extreme record this planet holds. Uranus holds the record for the coldest planetary atmosphere ever measured in the solar system, with temperatures dropping to around minus 224 degrees Celsius, colder than Neptune despite Neptune sitting even farther from the sun. Scientists still aren't entirely sure why Uranus runs colder than its neighbor. One leading idea is that whatever collision knocked Uranus onto its side may have also disrupted its internal heat flow, since Uranus barely radiates any extra heat from its interior, while Neptune radiates noticeably more than it receives from the sun. This extreme cold shapes the planet's pale blue-green color too, which comes from methane gas in the upper atmosphere, absorbing red light and reflecting blue light back out. Beneath that hazy blue exterior, scientists believe Uranus may hide deep layers of superheated, highly pressurized water, sometimes nicknamed an internal ocean, even though the surface reads as one of the coldest places any spacecraft has ever measured. All of these extremes, the cold, the tilt, the odd magnetic field, add up to a planet scientists agree deserves a much closer look than one 5-day flyby back in 1986. In 2022, the National Academy's Planetary Science and Astrobiology Decadal Survey, the report that guides NASA's mission priorities for the next decade, named a Uranus orbiter and probe as its top priority. Flagship mission for the 2023 to 2032 period. That recommendation reflects growing pressure among planetary scientists to finally send something back to Uranus after nearly 40 years of relying on a single brief pass. A dedicated orbiter could measure the planet's magnetosphere continuously over months or years instead of 5 days, catching normal conditions instead of rare, compressed ones. It could also study the moons directly for signs of ongoing activity, rather than relying on decades-old assumptions built on incomplete data. NASA has not yet committed a firm launch date, and any mission to Uranus would take well over a decade to reach the planet given the distance involved. But the recommendation has kept momentum building inside the agency and among the wider scientific community. The Decadal Survey estimated the mission's cost at several billion dollars, putting it in the same league as NASA's most ambitious flagship projects, and researchers have floated potential launch windows sometime in the 2030s to take advantage of favorable planetary alignments. Getting a probe to Uranus and into a stable orbit would also require dropping a smaller entry probe into the planet's atmosphere itself, similar to what NASA did at Jupiter with the Galileo mission, giving scientists a direct read on the deep atmosphere for the first time. Until a new mission actually launches, everything scientists think they know about Uranus rests on records collected during those 5 days in January 1986. Records that a small team of researchers just proved were far stranger and far less representative than anyone realized. Nearly 40 years after Voyager 2 sailed past Uranus, one of the most basic assumptions about the planet has been overturned, not by new data from a new mission, but by scientists finally taking a second look at data that had been sitting quietly in the archives the whole time. The planet wasn't broken or uniquely lifeless the way it looked back in 1986. It was simply caught during a rare, fleeting moment that happens less than 5% of the time. A moment that shaped nearly 4 decades of scientific understanding based on incomplete information. That leaves Uranus in a strange position today, a planet that's been badly misread for most of living memory, waiting for a mission that hasn't launched yet to finally show what it actually looks like on an ordinary day. If you enjoyed this video, make sure to subscribe, and I will see you in the next one.